Do people prefer the highlighting, or do we
Low.
prefer the low? Or take a vote? I tend to prefer the low, but
Then you have warmer excited.
hello. How did you hear about this? Oh, great. Great. All right, let's get right into it then. So, welcome everyone to session 2 of the Networked Imagination Laboratory's 2018 Haskell School. And in this afternoon's session, we're really just continuing on the stuff we worked on in the morning, just taking things a little bit further, and in particular looking at some types that are used quite heavily in practical work with Haskell. But before getting into that, I want to show a few more stuff about these type classes that we started to look at. In the morning, we looked at the type class show, and I want to look now at a few other common type classes. So one common type class that when we make new data types, it's really useful to add is the type class EQ. So I'm going to look for EQ on Hackage. This isn't quite the right place to look, but it will have the same stuff for us. So EQ is a type class for things whose equality can be compared. And the documentation tells us here that the minimal complete definition of it is the equals operator and the not equals operator. We haven't implemented that for the stuff we did in the morning. So I'm going to find what we did in the morning. Here's what we had in the morning. We had our new type live coding language we'd made as a way of representing that space. And we had our new type live coder as a way of representing a live coding performer who might use a live coding language. And then we had some examples of using that in some definitions. And if I fire up GHCI and load our work from the morning and do something like this, like compare the value supercollider to supercollider, you might expect it to work. It doesn't work. And look at that error message that we get. It says no instance for EQ live coding language. So because our new type live coding language, because we haven't made it an instance of the EQ class, there's just no way of telling whether these values are equal to each other or not. So just like we did this morning when we were first introducing type classes, let's follow that same pattern. Let's do it ourselves first in kind of the most naive, obvious way, but then later we'll just let the language do the work for us. But it's still useful to know how to do it kind of the low-level way, because you will certainly encounter circumstances where these things can't automatically be done for you. So we want to make our live coding language an instance of EQ. So we know that that's going to start like this: instance EQ live coding language, where? And then I'm going to go back to the documentation, which I guess I dropped. And it tells me that the minimum definition is the equals operator and the not equals operator. And I'm just going to copy those lines into my text editor as a reminder of what I have to do here. So I have to provide definitions for these two functions where the A in the type signature is not going to be A, it's going to be live coding language. So I'll indent 2. And I'm going to do this way. I'm going to do super collider equals super collider equals true. And super collider equals anything else equals false. And now I just have to tediously do this for all of the other. Hold on. Title cycles equals true. Title cycles equals something else equals false. Actually, as we're doing this, we probably start to realize we don't need to do all these false definitions. If we just catch the true ones, then all of the other ones will be false, right? So we'll do extempore equals true. Hydra equals true. And then we can just say anything equals false. And I'm just going to comment out the not equals thing for a second, and I'm going to load it. Oops. And it's even though we haven't done the minimal definition, it's not complaining. It's okay. We probably should do the complete definition. We'll do it in a second. So now if we type super collider equals super collider, we should get true instead, just like we would if we typed 3 equals 3 or whatever. So we've added, it's like we've added that behavior of being comparable to something else in terms of equality. We've added it to our type. And as a result of that, all kinds of other higher level functions that might depend on equality tests will suddenly magically work with our type as well. We'll probably see some examples of that later on. What happens if we try the not equal operator when we haven't defined it? I'm actually not sure myself. Well, it worked in this case. So this seems to be a slight little bit of slippage in the documentation there, because they say minimal complete definition is both of those things, but actually just defining one of them seems to be okay, which is more what I would expect, because usually the equals operation and the not equals operation are just the inverse of each other. So if you've got one of them, you probably have the other. So that's a really useful one. Another one that's really common is ORD. And that's for sorting things, comparing things in terms of whether they're greater than or less than each other. So if we look for ORD on Hackage, we'll come to a Hackage page about ORD. And I'll make the font a little bit bigger for people here. So it tells us that the ORD class is used for totally ordered data types. And basically, a totally ordered data type is something that you can sort. Like numbers, for example, are a good instance of ORD, because normally we can, given a random collection of numbers, we can put them back in some order from from least to greatest, right? And the minimal definition is one of these two functions, compare or less than or equal to. And if you look at the so what we're going to do is we're going to implement compare for our live coding languages, just to continue our theme of pissing people off. We're going to make the live coding languages greater than or less than each other. But before we do that, notice this type has an interesting feature, I think, which is that what we are going to have to do for our new type is all we're going to have to do is define compare. But if you look at the methods that are provided in the documentation, there's a bunch of them. And so that points to something, well, I kind of mentioned it a little bit a few minutes ago too, that like when we make our data types instances of these classes by implementing whatever the minimal function is, usually we gain access to a whole bunch of other things we can do with the thing on the basis of that ability that we provided. So it's really useful. We're gonna provide the compare definition, but max is automatically going to work for our stuff. So the other thing we should look at is the types here a little bit. So I glossed over that earlier, but in our EQ class, we were using Boolean types, bools, and there are just exactly two values for bool, false and true. And it's an algebraic data type, just like the ones we used this morning for the live coding languages. There's various stuff and various other functions that come with that type. Maybe we can look at that some more later. And there's also this type ordering, so we should look at that. So here's data ordering, constructors, LT, EQ, GT. So, and see that they start with capital letters. So this is also something that we glossed over a little bit in the morning, and I want to just, as a little tangent, deal with that now. Notice to point to some of the capitalization things here. So our type class, EQ, capitalized. Our type, live coding language, capitalized. Our constructors, capitalized. But our definitions, lowercase for the first letter, right? So those are rules. And if something, and basically what it means is that if something, we generalize a little bit here, something that is of value will have a lowercase letter for its name. Everything else will have an uppercase letter. Also, many of the Haskell keywords are lowercase, such as data or type or new type. Okay, so we're gonna make our live coding language controversially an instance of ORD. So instance of ORD, live coding language, and we'll just provide a definition of compare. So compare, the type signature is A to ordering. So I'm just going to copy that to my text to make notes about it. So it's in front of me. And then compare, and we're going to get two arguments. I'll call them X and Y. Both of them are going to be A's, which in this case means live coding language. And from that, we have to either make greater than or less than or EQ. So we could do this by doing things like this. Compare supercollider equals EQ. Compare supercollider tidal cycles equals, so here's where we get in trouble. We could make an instance of ORD where everything was just equal to be really democratic about it. It would be, I'm not sure it would really reflect the spirit of the type class, but there you have it. No, we'll just have to piss people off. We'll say tidal cycles is greater than supercollider. And we could compare supercollider to extempore, and we'll say it's less than, as kind of like compensation for the low cool factor score got in the morning. So it all works out in the end. So we could do that. You see that there's quite a large number of instances in that case, aren't there? Like, there's lots of combinations here with our 4 languages. There's 16 combinations, right? So let's rationalize it just a little bit. And it's a way of showing you another cool little piece of Haskell syntax called guards. So let's say that we're going to compare X and Y, and we don't quite know what they are. But we already know that live coding language is an instance of EQ. So we should be able to use the equality test function here. And the way we do it is with a guard. We put the bar in, and everything after the bar, but before the equals that's coming, everything in this space here is like a condition. And this particular definition only applies if that condition is met, if it's true. So we can do something like X equals Y here, and we're going to use our equals defined above in the EQ class. Then it's equal. And that counts for 4 of our definitions anyway. I'm not sure that it really makes the code that much clearer here, but it's a good excuse to show you guards. in Haskell definitions. So often useful. So now we have to make all the other ones. With your permission, can we not do that? Like, can we just say that we did it and not do it?
Yeah.
Pretend that we did it? Because it's sort of tedious. Anyway, we could do all those comparisons, and then we would be able to do things like sort lists of live coding languages automagically, and so on and so forth. What I'm going to do instead, more lazily, is I'm going to auto-derive EQ and ORD instead. Like, now, when you auto-derive EQ, it's kind of obvious how it's going to work, right? Like, if you compare two things and they're the same thing, it's going to be, yes, they're equal. When you do it with ORD, we can verify this, but it'll have to do with just the order of the list instead, which for many things makes sense. And if that makes sense, then do that. If you really need a specific kind of ordering arrangement between these things, then you're going to have to define compare tediously the way we were about to do. So let's do those auto derivations and get rid of our tedious manual derivations and then test it. So I've saved, I've loaded, and now when I type in SuperCollider, it should show automatically as a piece of text. Cool. When I compare SuperCollider to SuperCollider, I should get true. Yes, those are in fact equal. And if I ask if SuperCollider is greater than SuperCollider, it's not. Is SuperCollider greater than or equal to SuperCollider? It is. And if I have a list of languages, and I want to find the maximum between SuperCollider, tidal cycles, extempore, and Hydra. Here we're safe. We're not going to piss anyone off because it's just Haskell's auto derivation that is making the controversial decisions for us here. Apparently Hydra comes out on top. Let's take a moment to look at that maximum function. So I could go and look in the documentation for that, or in many cases, especially when it's kind of essentially a built-in function, just using :t at the GHCI prompt is enough. Let's look at the type of maximum. So like we've been doing in the morning, let's start by ignoring everything to the left of this funny-looking arrow and just look at this part, which is more like the arrows we've talked about so far. So it says TA to A. Now let's look back. The T says foldable. Just take my word for this for a second. Well, for more than a second, maybe, for a day or two. The T there is basically, for our purposes, this means like a list. So you can read this like list of A to A. And then notice how here it says ORD A. So basically what it's telling us is that the A's in this definition have to be instances of the ORD class for this to work. So if you have a list, and if the types in the list are already an instance of ORD, then the maximum function will work with it. And like just intuitively that makes sense, right? Like if I gave you a bunch of stuff and I asked you to sort it, you would only accept that task if the things were actually comparable to each other, right? You'd say, yeah, like if you could, if I said, like I gave you a bunch of blocks of different sizes or something like that, we said sort this by size, The blocks are comparable in terms of their size. In other words, they're instances of ORD. So that's ORD. There are a few other common ones. One that is kind of interesting, another interesting type class, is num. I don't want to go into too much of this because it gets a little bit complicated. But if we look for num in Hackage, is it here in the prelude? So I hope you can all see that. So there's this class num, which it says is the basic numeric class. And now we saw this a bunch of times in the morning. That's why I wanted to come back to it. Remember, like when we did this, when we asked for the type of the number 7 at the prompt, instead of just saying int or something like that, it says num t. So the way that we read this, it's like saying 7, well, it's some type t, and we don't know anything about it except that whatever type it is, it's definitely an instance of num, is what it's saying. If we did this instead, if we asked for the type of 7 and we put a type annotation on it, then we'll just get 7 is an int instead. We'll force it to be that specific type. So basically what's going on here with the num class is that when something is a number, like there's different types of numbers, but all of these different types of numbers have this kind of Venn diagram of overlapping common things you can do to them, right? Like if something is a whole number, we can add it to another whole number. But we can do that with fractional numbers too. And we can actually do that with imaginary numbers as well. Like they all have that operation of addition available to them. Now, it works in different ways for all of them, right? Like addition isn't the same for these different types of numbers. But it is there, and conceptually it works in a similar, it's analogous, right? So that's a good clue when you see something like that. Like you have different things, but they all have a similar behavior. That's a good clue that you're dealing with something that is a type class, right? So in Haskell, the numeric types are partly organized around a couple of these type classes. So let's look at num. It says basic numeric class, minimal definition. You have to provide plus, multiply, absolute value. This tells you what the sign is it positive or negative? And you have to be able to convert it from an integer, and you have to be able to negate it. So if your type can support all of these things in some way, then you can make it an instance of the num class, and that means that you can add them to each other and subtract them from each other, and that should be meaningful. I think we'll come back to this on the last day because this is used in elegant ways currently in title, for example, to allow different title patterns to be added and subtracted and multiplied and all that kind of stuff from each other. And that's an interesting example because title patterns they're not numbers, but they can still be an instance of the number class because it makes sense to support these operations on them. So I guess in a way I suppose that means that title patterns are numbers in a way. Like if we can do all the things that we do with numbers with title patterns, I guess they are numbers. Not everyday numbers though, I guess. Anyway, we're not going to implement that now because that would be a pain, and it wouldn't make much sense for the types that we have here anyway. But if we, I did want to kind of flag this for you because in practical Haskell programming, where you'll find yourself looking at this page is when you need to convert a number from one type to another. Because a lot of the conversions between different types of numbers in Haskell are managed through the definitions in these type classes. So you'll find yourself digging through this documentation to convert, an integer into a float, or a float into an integer, or a different type of integer into a different type of integer. A lot of that stuff is managed through here, and so it's useful to just be familiar with this kind of documentation. So, for example, for the class num, it provides these methods, including the class from integer. So that means that if we want to convert something into some class, and we're able to have an integer representation of it, from integer should be the last step in our little conversion that we're doing. And you'll find other little things like that there. And then if you here you see the list of instances, and that's super useful. And it's a lot like what we saw with EQ and show. Like most of the built-in types that have a vaguely numerical interpretation are instances of num, which means that from integer exists for all of them. So for example, a double, which is a high precision floating point number, is an instance of num, which means that you can call from integer on an integer and get back a double if you need to in some circumstance. I'm using footnote here, in my language there, I said you can call from integer, and that's kind of, I think, a sort of bad, well, can I say bad habit? A bad habit from my early days of imperative programming. It's not really that we call this function, it's that it just gets used in the compiler's generation of our code. I don't know, are there other useful, people here in the crowd? Are there other favorite type classes that I'm missing? I think those are the basic ones. Yeah.
This is a language, and languages can be composed, all right?
Yeah, we can look at monoid. I don't know how we'd apply it to this particular example, but let's look at it anyway. So a monoid is something where, let me give you the off the top of my head explanation first. A monoid is a type where you have an operation that you apply to the type that gives you back something else of the same type, and you also have a value of the type that when used in that operation doesn't make any change. So a simple example of a monoid is addition. So if we look at numbers as a monoid according to addition, the operation is addition, and the neutral value is 0. Because if you take 4 and you add 0, you just get 4, right? Whatever you add 0 to, you get itself again. So that pattern, that's the pattern of what's called a monoid. And if you know that something is a monoid, there are various other convenient operations that potentially become available to you. And so, of course, we're gonna, in Haskell, we could declare something as a monoid by providing the function providing a definition of mEmpty and a definition of mappend. So I'm not quite sure how we would do that for our live coding languages. Like, what does it mean to combine live coding languages, these 3 live coding languages?
You just say take 2 languages, and then when you combine them, you get a third language. Or that a third language can be the result of combining
Yeah,
existing languages.
sure. So, okay, let's do it. We're going to really be departing from the real world semantics of these languages. But let's run with the example. Let's imagine that any two of these languages can be combined, and what you get is another language from the list. You know? So actually what we're composing here is a weird kind of graph that you can traverse here. But so we're leaving the real world a little bit here, but it's okay. It will be fun.
Isn't this kind of real world?
No,
It's a composition of
I'm not.
functional and imperative stuff.
Yeah, no. When I say we're leaving the real world, what I mean is that because when you combine super collider and tidal cycles in the real world, that doesn't work. Like it's not an actual monoidal operator. Well, no. See, what I mean by real world is actually the real world. Like super collider is a language, tidal cycles is a language, Hydra is a language. They don't combine to form each other. So we're making it up here. It's exactly. We're gonna exactly. Exactly. We're gonna pretend. That's what I mean by leaving the real world. So instance of monoid live coding language. Where? So mEmpty has to give us the unit that, when combined with mappend, gives back the same thing. So basically we're saying one of these languages, when you add it to any of the other languages, has no effect. on the other languages. We could add another language. Let's add another language. We'll call it empty language, because it's a language that has nothing in it. So it's a good choice for a monoidal empty. So empty language will be our monoidal empty. And now we have to define mappend. And we can define this however we like. So if you do super collider and tidal cycles, for this to be a strict monoid, you have to get something different than what you put in. So it can't be super collider and it can't be tidal cycles, because the only one that doesn't have any effect is empty language. So let's say super collider and tidal cycles gives you extempore, and let's say tidal cycles and super collider also gives you extempore. So this is kind of like addition, in that if you turn it backwards, it's still the same thing. And let's say if you do tidal cycles and extempore, you get hydra. And if you do tidal cycles and, extempore and tidal cycles, you get hydra also. And if you do extempore and hydra, of course you get super collider. And vice versa. And there's a few more combinations. Unfortunately, there's 16 of these. Well, maybe let's leave it incomplete. Let's just put that much. And then when we reload it, it's going to be fine. Now, the whole point of a monoid is that, or one of the points of a monoid is that you know that you have a way of combining these things, and you know you have a value of these things that has no effect. What this lets you do is automatically do things where the things are combined and we get some kind of sum value of a group of them in a meaningful way. So because our live coding languages are instances of monoid, they can be basically combined, they can be appended with another one in a particular meaningful way. That's the idea. So we can take a list of them, and we can use mconcat, which if we look at its type for a second, it takes a list of A's and gives you back an A, and the A has to be an instance of monoid. And basically what it's going to do is it's going to combine all those A's using your mappend operation, and in that way you're going to come up with a summary value. So we can take the mconcat of our list of languages, tidal cycle, super collider, hydra, extempore, and well, it didn't work in this case because we didn't provide all of the definitions. So somewhere in there we hit a set of pairs that we didn't provide. But I have an idea of an actual use of monoid we could do that would make sense, because I just realized that this monoid setting mirrors the exercise we did at the end of the morning too. But there was a question first.
So for the mconcat, how would it work? Like, does it use the first two and then finds an answer and then uses that to do the next one and the one that it made? Like,
I believe so, yeah. So I think in this case what's happening is we're getting mappend called on tidal cycles and super collider.
kind of like
And that
fold
gives
L?
kind of like fold L, exactly, which is why we can go back to our example from the morning with this approach instead. So I think it's giving the exception because tidal cycles and super collider is extempore, and then extempore and hydra is super collider, but then super collider and extempore is not defined. But anyway, let's go back to our example from the morning. So let's leave this one behind, and let's go to what we were doing in the morning. So we had our ensemble cool factor, and we're using fold L in the end to define this. But we could, and our ensemble is a list of live coders. But if we made live coder an instance of monoid, then the definition of this would be really straightforward. We're making some assumptions here, but we'll talk about that in a second. So let's make live coder an instance of monoid where m empty. No, wait a second, we can't do this. For this to work, we would have to be able to define a live coder whose contribution to the ensemble was 0.
Can we?
And that doesn't seem like a really nice thing to say.
But
So maybe we shouldn't do that either.
we have the empty language, so we can make a live coder whose name is the empty string and whose language.
Okay, good. I like it. Yeah. So if you're a live coder and your language is empty language, like, you suck. You are not helping the ensemble. So you're the monoidal empty. So we'll make a cool factor of 0 for empty language. There we go.
I mean, it's a pretty cool language.
It's exactly.
The empty.
It's conceptually cool.
Yeah, I mean, like, we had to go and make it. That's how cool it was.
Yeah. So mEmpty. So our mEmpty actually has to be a value. If live coder is an instance of monoid, then our empty value has to be a live coder. So let's make a live coder whose name is just an empty string and whose language is the empty language. And now we have to define mappend, and it's going to take 2 live coders. We'll call them x and y. And this isn't going to work either. Because what we have to do is we have to be able to provide another live coder whose cool factor is the sum of the other 2 live coders' cool factor. And we don't have any way of doing that because of our language type, unless we make a really twisted example.
But why does the sum of their cool factor have to be the cool factor of the resulting combination?
Well, because that's what we're trying to do, is find the total cool factor of an ensemble. That's the exercise we did in the morning.
Okay.
Yeah. I think we should probably abandon this example a little bit, but it's okay.
Wait, I'm sorry. Oh, the cool factor is not a part of the live coder. So there's no
Exactly.
cool factor.
Yeah.
Oh, okay.
So I think this has been a useful tangent, like, because monoids do come up and they're often useful, but there are also lots of situations they don't really apply to too. Like, let's think again about the textbook example I gave, like addition with numbers. You have a series of numbers and you add them to sum them and you get a number. So you're getting another one of the same things you're getting. So that the monoid pattern is always this pattern about you take things and you combine them to get another of the same thing. And when things depart from that pattern, you're probably not dealing with this this type anymore.
It's kind of like the 0 vector in like linear algebra, where like one of the axioms is that for it to be a subspace, like if it has a 0 vector, then it has to add with that definition of something to make the same thing.
I am super rusty on my linear algebra, but I think so.
Yeah.
Like it kind of vaguely rings a bell. Sounds like the right idea. Okay, so enough about that. So briefly, continuing a little bit about higher order functions. So we saw this morning, and we used it. We saw this operation, the compose operation, the dot. And if we ask for its type at the terminal, it looks like this. We didn't look at that, and this is actually, we should have, because it's actually useful. So if you look at the type for dot, it takes a function from B to C, a function from A to B, and basically gives you a function from A to C. And one thing I want to kind of call your attention to is a nuance of the way this is written here. Like, look at the way I read it versus the way it's written here. It takes a function from B to C, a function from A to B, and gives you a function from A to C. But look at the brackets. Like, I didn't read the brackets exactly there, or I did and I didn't, right? Like, the one at the end isn't in brackets, and the ones that in the two at the beginning are in brackets, right? In other words, this is what's written there. I'm going to write this out a different way. What is not written is this. This is wrong. And let's think about why. That is something totally different from function composition. Because what this is this is a function that first it takes a B, then it takes a C, then it takes an A, then it takes a B, then it takes an A, then it takes a C, right? We could also say it's a function that takes a B and gives you a function from C, A, B, A, C. Or we could say it's a function that you give a B, a C, and an A, and it gives you a function from B to A to C. Like, all of these readings are equally correct. But the actual composition operator, I'll delete the incorrect one there, puts those in brackets. So basically it's saying that the first argument of the composition operator has to simply be a function from B to C. And the second argument has to simply be a function from A to B, whatever B and C and A are in this circumstance. While we're talking about that, though, because this is useful a little bit, let's say that we have a function f that goes from A to B to C. This is equivalent to this in Haskell. So if we have a function that goes from A to B to C, it's the same thing as a function from A to a function from B to C. Let's just develop this idea a little bit using maybe the plus operation. So plus is an operation from A to A, where the A's are all number, right? If I take the type of 3 plus, so I'm using plus, but I'm only giving it one argument, this is perfectly okay. It's a function from A to A. It makes sense, right? Like, plus needs two arguments. To do plus, you need two numbers. But if you've already got one of them, like if what you've got is 3 plus, you only need one number to finish this off. So this is actually a really, really common pattern in Haskell, and so it's got a name. It's called partial application. We've already kind of seen it because we were talking this morning. We did some examples where we were talking about like types being stripped off the type as things got applied. So we're really just looking at this again here from a slightly different angle. When you partially apply something to a definition, what you get back is a function. And so because of that, that's why these two things are equivalent. I don't know that we need to say too much more about that. Okay, so I want to talk now about curried versus uncurried functions, which is a way of coming back to those tuples that we were looking at before. So let's imagine that we well, I'm trying to think of a good live coding example of a tuple. We'll make some function from a tuple to something else. maybe it's a function from. We don't want to be controversial. We'll make it. Basically, we'll say that this is a. The first int in the tuple is your street address, and the second one is your personal live coding cool factor. And from your street address and your personal live coding cool factor, we are able to determine with 100% scientific accuracy your chance of becoming world famous as a live coder. So we'll call the function.
That's also controversial.
Well, only secretly, because notice how the street address is random. So we're basically saying it's random. Yeah. We'll call the function how famous will you be. Sounds something like from Dr. Seuss or something. And it'll take a tuple of 2 ints, and it'll give us back an int. And now we could define this in different ways, but for now we'll just say, we'll be lazy, and we'll say that how famous will you be, address and CF for cool factor equals your address times your address times your address minus your cool factor times your address plus your cool factor times your cool factor times -1 divided by your address. Let's live dangerously. Just got a misspelling there. I'm pretty sure that is the scientific 100% guaranteed formula for how famous you will be in the live coding milieu. And let's test it. We should always test, so we'll reload it. Oh, mappend is not. Oh, we got to abandon our live coder monoid here. Okay, now we'll try again. Oh. No instance for fractional arising from a use of divide. Oh, right. Divide works funny with ints. Let's just get rid of the division. I'm pretty sure that more multiplication is actually the correct live coding famousness algorithm. And we'll reload it. And we're fine this time. And so now we can use it. How famous will you be? And we have to provide a tuple. It could be like your street address and your cool factor. And there you go. You know, I'm going to be very famous. But let's look at the type of how famous you will be. Again, so int, int, int. And in this definition here, notice that we could have done this a different way. We could have done this like this instead. And I'm going to call this how famous will you be prime. So that's kind of a Haskell custom or convention. If you've got multiple versions of the same definition, as a lazy way of keeping them separate, people will just add a little quotation mark after it, and it's said prime. So it's like F prime, F double prime, F triple prime, this kind of thing. So how famous you will be prime, it does exactly the same thing, but it's organized in a different way. The type signature for this one looks like that, right? It takes 2 arguments and gives you an int. So, and it would. So here we go. I'll save that. I'll load it, and for that one, I have to provide the 2 numbers separately. And oh yeah, thanks. Exactly. So there we go. We get the same answer, but the type of the definition is different, and the way that we use it is sort of superficially different as well. So this is kind of an important thing to note here, I think, which is that both of these make sense, right? Like they're both perfectly reasonable definitions. In the one, you have to provide this thing this tuple that is at the same time an address and a cool factor, and in the other one you have to provide an address and a cool factor, but they're not bound together as a tuple. And so the point here is, so what? And because that, like, there's no answer to that. Really, there is they're the same. They're just different ways of notating and organizing the same thing. Haskell provides ways of flipping between these different representations of functions. And this is what, this is called currying and uncurrying, which has nothing to do with spicy food from Southeast Asia. The Haskell is named after a mathematician whose last name was Curry. His first name was Haskell Curry. So they called the operation curry and uncurrying. There you have it. So if we look at the type of curry, curry takes a function from a tuple to a value and gives us a function that takes two arguments to give us a third value. And uncurry is the opposite. It takes a function that takes two arguments to give us a value and gives us back a function that takes a tuple to produce a value. So in that sense, this one here, our tupled one, is the uncurried version. So if we wanted to, we could instead comment out this definition and make how famous will you be, the curried version, by applying curry, like calling curry on how famous will you be prime. And when we reload, oh, it's still not happy. Oh, I have it the other way round. Sorry. Uncurry. There we go. Because these two functions are really the same. Whether we prefer the curried or the uncurried version of them, conceptually they're the same. So, so anyway, in practical Haskell code, you will encounter things that are curried and you'll encounter things that are uncurried, and it won't always be up to you which way something is, like because someone else wrote it and they're sticking to it, it's your problem that it's not the way you like it. That's okay. You can use curry or uncurry to take their function and turn it into what you need in this particular context. So it's useful to know, comes up from time to time. And also as a kind of meta observation, when we used uncurry here, I think that's a very typical higher level functional programming concept or practice there. Like we took an existing function and we did something to it with a function to get another function that we didn't write or didn't specify, right? And we'll see more examples of that, I think, as we go. There's a few more like this. This one's kind of trivial. Let's make a how famous will you be prime, double prime, and this one, in this one, the order of the arguments is reversed. So your personal cool factor comes first, and then your address comes. Now we could make this by just copying and pasting. That would be one way. That seems pretty bad style. Don't do that. Don't copy and paste. Why not? I mean, I suspect lots of people know this, but in the context of software development, as opposed to, say, live coding musical improvisation, copying and pasting is dangerous because you're taking the stuff that you haven't necessarily understood or parsed or are looking at, and now you're putting it somewhere different and hoping for the best. That doesn't seem like that's going to go well, and generally it doesn't. So we're definitely not going to do that. So then the next thing we might think of might be this. So we just call the other definition with the things flipped. That works. That's okay. That's not terrible. You'll see lots of that kind of stuff in practical Haskell code. But hopefully you're hearing the punchline here. Even though that's not terrible, it's okay, it's clear, I don't mind it. It's not very high level, it's still kind of obvious, right? Surely there must be a cool, hip, Haskellian way to do this. And there is, and it's another high level composition, higher level functional programming type thing. It's called flip. And if we look at the type of flip, it takes a function from A to B to C and gives you a function from B to A to C. So basically, it's with functions of 2 arguments, it flips the arguments. So our best answer here is going to look like this. How famous will you be equals flip how famous will you be prime. And notice how the parameters disappeared in this definition, because we're just following the type signature of flip, right? Like flip, the first argument is something from A to B to C. And we provided that in the form of how famous will you be prime. And then from that, you get B to A to C, which is what we're looking for. So we're done. Okay, there's one more of these high-level operations on functions that I want to show you, and then we're done this section. And we've actually already used it, so I'm just coming back to it now, sort of for real. And that's the operator $, which actually, it turns out, is not just a kind of random symbol. It's a definition, like all of these things in Haskell. And the type of it is you give it a function from A to B, and it gives you a function from A to B. But basically, what's happening here is like it's applying the thing in A to the function you provided to produce B, which almost as a side effect has a consequence of removing the brackets in a lot of those expressions. Like, let's go back to how we saw this being used. We saw something like, we have cool factor. That's not going to work. Yeah, we did like, so Dr. Zero was a live coder, and then language Dr. Zero was my language, and cool factor of the language of Dr. Zero might be an expression that we might write, right? And we saw that we could also write this expression this way, and now maybe that looks a little bit different to us when we look at the definition of $. So let's look at it. So $, its first argument has to be a function from A to B. That's what cool factor is. Its second argument has to be an A. So all of this, which is a live coding language, is the second argument, and we're done with no brackets. But there are circumstances where it's useful to keep in mind. Let's drop it for now, but you'll definitely encounter circumstances where remembering that $, is actually this function that applies a value to a function that you provide to give a value actually is useful. So that's all very abstract stuff. How are we doing? We're kind of going to move into a new section now, but are there any questions or?
I have a question.
Yeah.
Is the $sign an infix function?
Yes. So the question is the $sign an infix function? And your question reminds me that there's something we've been glossing over here with some of these functions. So many of our functions are what we would call prefix functions. So like cool factor, for instance. We write cool factor, and then after it we provide the argument or arguments to give us the value. But some of our functions, some of our definitions are infix functions, and what that means is that they take 2 arguments and they go in between the arguments, like 3 plus 4. What's the type of plus? Well, it's from A to A to A. But it's an infix function because the plus goes in the middle of the 2 things. and this doesn't work. Except there's a way to make it work, right? If we want to take an infix function and we want to use it as a prefix function for whatever reason, we just actually wait a second. Am I telling you wrong? No, I'm telling you wrong. It's what I want to show you is the other way around. If we have a prefix function and we want to make an infix function out of it, we can put it in quotes. So, well, have we defined any? Well, how famous will you be? So, let's say that your cool factor. Let's say we want to try to do this. Your cool factor. How famous will you be? Double prime, and your house address. That's not going to work. But if we put that whole definition there, the name of the definition, in back quotes. Oh, it's not in scope. Let's try the single quote one. The single quote one worked. Not quite sure why the double quote one didn't work, but I don't think it's important. Let's leave it. Anyway, that's the idea. So you have a prefix function, you put it in back quotes, and you can use it as an infix function. There probably is a way of doing the reverse as well. I'm not sure what it is off the top of my head. Does anyone know?
It's like brackets with like a dollar sign.
Oh, of course. Sorry. Yeah, we're doing it all the time. Yeah. So an example of that, I guess, would be using plus as a prefix function. There we go. Yeah. Yeah, Luis.
Sorry, and I asked that because you just realized that when you were using I realized that the dollar sign was an infix function, or thought about that because you were, when you were explaining that it was like in between the first function, like when you were showing the type of the dollar sign, it was like in between this function and then the next function, I guess. But it also works when you put it in brackets and at the beginning.
Right.
But it seems redundant because then you have to put a parenthesis like other brackets in one of the functions.
Possibly, yeah.
Yeah.
I think the question is about using the comment is about using the dollar sign definition at the beginning as a prefix operation, and how maybe that's kind of redundant. And yeah, I think maybe it is. I'm not sure. I'm not super sure, but
it is because the dollar sign basically means from wherever you put it to the very end of the function, right?
yeah.
Just put brackets at the end of the function. What's the point of the brackets?
Yeah, so if we put dollar sign, now we'd have to provide a function. So it could be cool factor, and then we'd provide some value for cool factor, and this is just the same as that. So yeah, I don't think I've ever seen it. Anyone try it either in the wild. All right. We've been going on for about an hour, and that's some fairly abstract stuff. The rest of what we got today is a little bit more concrete and down to earth. Should we take a break? 10 minutes? All right, let's take a 10-minute break. And we'll come back at 3:10. I might go get some fresh air. Is anyone going to stay in here?
Yeah.
Are a few people going to stay in here?
Yeah.
All right, we don't have to lock it then as long as someone's in here.
Yeah, that's what I'm gonna do too.
Yeah.
Because this one's super hot. And
I like it though. I like the environment's quite interesting. But
why can't we go somewhere else? I mean, this.
I need to like stand up. The thing is, I was like, I need to get out of the house because I just stay at home and I just.
Wait, you
sit
commute,
or-
right?
Yeah,
From where?
from downtown Hamilton. So I was like, you know what, I need to get out of the house, and then now I'm still sitting. It doesn't make
Yeah.
a difference.
I mean, when I'm at
It's,
home, I'm watching TV or something.
Yeah, but the thing is, like, when I'm in an environment like this, I cannot be distracted. You know, like, I don't know. It's
Alright, you guys go outside. I'll stay
No,
in here.
you
I'm
stay
not going-
outside.
no,
No one's gonna come in if we're on the door.
no, I'm not going outside. I just want to stand up because I feel like I'm gonna.
It's so hot here. I'm actually gonna. I don't feel that hot. Not gonna lie.
Bring a freaking hoodie.
I know. I don't know why. I'm feeling fine.
You get used to it, I think. Initially, when I walked in, I was sweating, but now I think I'm used to it.
The guy was sweating too. Yeah.
I mean,
Yo,
yes,
in Mills, like there's literally like nobody, and we can just go there as well. Like,
Mills is the nicest place when it's empty.
yeah.
So nice. But then people come and they destroy it.
Yo, look outside. It had been empty the whole time at Mac, and now there's like a zillion people.
Yeah, I know. I'm so not used to it.
Yo, me too.
I know, and I was like, you guys, we're being invaded by first years. It's like.
I mean, we were first years last year. We were
I
exactly
know,
there, but it's still annoying.
Mhm. And it feels weird looking at them and knowing that they're young. You know when you can tell that someone's older than you,
Yeah.
and you can tell that someone's younger than you.
Yeah.
It feels weird being
The
looking
older.
at someone and being like, why am I the older one? Why are they the younger one?
Yeah.
Oh my god, my muscles are like done because of the thing. Oh, you know how famous Soy the Bee thing? You
Yeah.
know how I got a negative 400 from my first try. It's like negative. Okay, fine. Sure. My brother called me.
Do you want to be famous?
No, but like still, it still.
It hurts,
feels-
it hurts.
It still hurts when it's I mean, look at it's negative 260. Like there's no way on earth that you will be famous. It's like God.
Yeah.
It's like tear falling down. I had to call my brother because he called me and be like, Muhammad, I'm good. When did the Haskell thing until
5.
five it is. لغاية 5. Yep. لا مش حلو بس اليوم حلو غير باقي الأيام مش حلو. Nope. بقول لك بعدين. بقول لك بعدين. I'm so used to the weather. Right now, with the temperature right now, I think if I go outside and I come back, I know it will be worse.
Yeah,
So I'm just gonna
it is
stay.
worse.
It feels worse now, right? Okay.
Yeah, but I really needed the outside. Why did I leave the door open? Would that help?
I don't think so, no, because it's a pretty secluded. Like if it were, I don't know, because it will come just to the side, right? There's so
But aren't
many
there
wires.
supposed to be 2 doors here, Yamna?
There are. There's one more.
Where? Like, so freaking black.
That one.
That's a door.
That's where we tried to enter.
No, it's not. There's nothing
Well,
here.
because I have research assistants working on
It's
our
supposed to be on that side,
developing
so
languages. So for us, a bunch of people here are those research assistants. So it's like a chance to
I
get the
haven't
team
even
on the same
been
page.
listening enough time.
But then it's like, if we're going to do it, we might as well open it up, right?
I literally only
And if someone does get interested and joins the orchestra,
But
we're happy to do it.
And
I think a few people in the
there's
computing would
another
be
one.
happy
I
to-
forgot the name.
Well, yeah, that would be great to connect with them.
The newest one.
If this was posted on like a Facebook group,
Yeah.
like Class of Engineering 2021 or something, I think there would be more people.
Sure.
Yeah, because I only found out about this because my prof told me that there was an opportunity and you should go,
Right.
but it wasn't like
Right.
openly told to everyone.
Right.
So that would have been.
Sure. Well, and it'd be great to tell people in computing about the laptop orchestra here, which is the group that occupies this space a lot of the time, making music with programming languages.
Also, Dr. Anand,
Anyway, we can talk about that after. Right now, our internet audience is expecting us. How many thousands of people, Luis?
3,000?
3,000.
there's 3,000 people watching it.
Yeah, give or take.
To the
Take
power
and
of-
take.
You didn't have to like break the illusion there, you know.
10 to the power of 3, of course.
We could have been like 3,000, and then we just left it there,
Yeah,
and then had everyone believe there's 3,000.
that's right.
They can tell though online.
Or they can just not go online, and we keep on fooling them for a very long time. And then as the days go by, we say that the number of viewers increase. So like tomorrow it's 4,000, and the day after it's even more.
We'll get there. We'll get there.
Probably, yeah, of course.
Why are we not going viral? I don't understand.
You haven't made a pop hit yet.
How could a 1-hour treatment of curry, uncurry, flip, and function application not be a hit?
If you name it Flip and Curry, guaranteed.
All right, so we're going to continue now, and I wanted to start by taking a little detour and talking about Haskell modules. So far, everything we've been doing, we've been working in this text file that we gave a specific name, and we loaded it directly at our GHCI interpreter at the terminal, and that was enough. But typically when you're making software, that's not enough, because things grow and they get more complex, and so having some way of breaking them apart and putting them in separate modules is super useful. And so every language of any sophistication or scalability will have some kind of system for putting software bits in different places to kind of keep them separate from each other, and Haskell is no exception. We can make a module in this system by heading our document with the module keyword and then giving it a name. The names have to start with capital letters, and they can also be articulated by periods if you want. Like, for example, we could maybe call this module live coding language, or if we wanted to make an articulated name, we could call it maybe something like languages.livecoding, because maybe there are other modules for other languages. I don't know. When we come to the point where we are writing Haskell programs that run in some execution environment, like we're writing a program to run at the command line, or we're writing something to run in the web browser, like we'll get to later in the week, using different compilers and build systems, then we need to have at least one module. We need to have a module called main, which is where the build system will go to look for the overall program that you are trying to build. So we could call our module main here. In fact, our module was already implicitly called main. If you look down at our terminal, see how it's been saying main here all the time at the prompt? It was defaulting to calling our module main because of that. So that's making a module, the short version of it. It's also useful to import modules. One module we're going to import here in a second is the one that's called data maybe. So I'm going to do the import first, and then we'll look at what we can do with that. So that's what importing data.maybe would be. And having done that, all of the definitions that are exported by data.maybe will become available to us in this module where we're working. And there are literally thousands of these Haskell modules. And so once you're doing anything that's non-trivial, typically looking through the documentation of modules and reusing existing modules becomes a pretty key everyday part of working with this. And perhaps this goes without saying, but sometimes when you're learning these things, you may think that, oh, I'm having to look this all up. I'm having to look this stuff up all the time in the documentation. I must be an idiot. I'm a terrible programmer. And it's important to realize, no, like reading that documentation and interpreting that documentation is a significant part of the act of programming for everyone. So, that never goes away. There's thousands of them. They change sometimes. You just have to look it up. The skill isn't so much, let's say, writing the right thing. The skill is in reading and interpreting in order to figure out what the right thing is. Anyway, let's look at the documentation for data.maybe. So as is my habit, I'm going to search Google for hackage data.maybe. I'm sure there's a way of doing this that doesn't depend on Google, but it's not my habit. And we get the documentation for data.maybe. And it tells us that this module provides the maybe type and associated operations. And in the top left corner, you see here it says base 41110. That's actually a significant piece of information. What it's telling us is that this module is part of the basic set of libraries that comes with the Haskell compiler or interpreter. So we don't need to install a library or a module to use this. We don't need to install another library to use this module. We should already have it. If we don't have this, something has gone horribly wrong with our installation of the Haskell platform. Probably best to nuke it all and start over again in the unlikely event you encounter that. For other types, we might find something different. Let's look for so let's say I just picked this example at random. We'll come back to this later. Let's say that we needed the module control monad.state, which provides all this yummy stuff. We can see here from the documentation that this is in the library MTL. That's not installed necessarily by default. It might be, depending on what kind of installation you happen. And if it wasn't installed, with a normal Haskell platform, you would use Cabal to install it. Cabal is the package manager for Haskell. So if we did Cabal install MTL, which is the name of that library, it's going to trundle off and look at a database, figure out what the appropriate version of this library is for you. It's going to install it, and then that module control monad.state should be available for you, in your Haskell programs you write from that point on in that environment. I bet you this is going to tell me it's already installed. It's going to warn me I haven't updated. It says all of the requested packages are already installed. It tells me the version that's installed is MTL 222, and here that's the most recent version on Hackage 2, so we're good. I already got this. But if you didn't already have it for some reason and you tried to use it, you might get some error. Often these error messages are quite helpful. Usually they'll often say oh, we didn't have this module, but are you sure you don't need to install this library? They do have some of the common ones covered with helpful error messages. Anyway, for the one we were looking at, data.maybe, we should all have it already. Just going to reload my oh yeah, right. So I just loading my file there, I just remembered that if you do say that your module is called main, you have to provide a particular definition called main as well. So I don't want to do that, so I'm just going to delete my module declaration for now. So our task right now is to look at maybe. So like it says here, the maybe type encapsulates an optional value. A value of type maybe A either contains a value of that type or it is empty. Using maybe is a good way to deal with errors or exceptional cases without resorting to drastic measures such as error. So essentially, when we're dealing with a maybe, we're dealing with something that might be there or might not be there. So this is a really, really common case that comes up with, right? Like imagine we're collecting data about something. Go back to our live coding example. Imagine we're dealing with the live coder's language. What if some live coders don't have a language yet? Either because we don't know it or because they refuse to declare allegiance to a single language. Those are my kind of people, by the way. How would we represent that, right? Let's go to our live coder here. So we have live coder string language live coding language, but our only values for live coding language are these. And empty language, unfortunately, and doesn't capture our situation here. In fact, let's just delete it anyway, so we don't get confused by it. So our languages have to be these things. Now, we're trying to represent what happens when someone doesn't have a language. So you think, well, we could add it. We could add another type here. Doesn't have a language. But that doesn't really make sense. Like, the type is a live coding language. It's not the type is live coding language. Super Collider is a live coding language. Tidal Cycles is a live coding language. Extempore is a live coding language. Hydra is a live coding language. Doesn't have a language? That's not a live coding language. So we've already, like, if we do this, we've made a kind of weird decision already. And I bet you it's going to come back and bite us later on. Because how is it going to come back and bite us? For example, we're going to have to provide some kind of definitions about these things, about ways of combining them, about ways of doing things. And then we're going to have to provide that for doesn't have a language, and it just isn't going to make sense. And our system is going to get confusing. Either we're going to fail to implement something, we're going to make mistakes, who knows, right? We're making a mistake because we'd be fudging, we'd be compromising there. We're like, oh, we need to cover this situation where they don't know the live coding language. And instead of actually covering that situation, we're changing something else. Like we have this nice, pure type that represents our possible live coding languages. And instead of actually dealing with that, instead of actually dealing with our problem, we're messing up that type. So what we've done here with doesn't have a language, that's a mistake. We don't want to do that. What we want to do instead looks more like this. Because now nothing changes about our live coding language type. But around it, we have built another type, which is maybe one of those, or maybe not. So some valid let's leave our text document aside for a second and just and actually I'm going to delete what I did here for a second just to be able to reload. So Super Collider is a live coding language, and I can find its type here. Whoops. Just Super Collider is the value just Super Collider, and its type, whoops, is maybe live coding language. And the type of just extempore is also maybe live coding language. And the type of nothing, which is a constructor in the maybe type, is maybe A, where A can be anything. And we can also, if we want, we can do the type of nothing, where nothing is of type maybe live coding language. And then trivially, the type of that is maybe live coding language. So I think the thing to do here is to rework our example from the morning using maybe, just for a second, I want to go back here to the documentation and just point to you that this type, this data declaration, looks a little bit different than our ones this morning. It's got this variable a in it. Like if you look at our one here for live coding language, it just says data live coding language. Like our type is live coding language. There's nothing else to know about the type. If you have a live coding language, you have a live coding language. But for maybe, it's not that straightforward. You don't just have a maybe, you have a maybe a maybe of some type, like a maybe live coding language, or a maybe an int, or a maybe a string, or a maybe a bool, right? In this case, there are no constraints on what that second type can be, what that type variable applied to maybe can be. And that makes sense, right? Like obviously, for pretty much anything, we can say that you maybe have it or you don't, right? But look at the way the a flows through here. So the maybe type has two constructors that we've seen both of them already, nothing and just. So the constructor for nothing is just nothing. It looks just like our constructors over here for supercollider, tidal cycles, and extempore. But the constructor for just is the word just and then a. And the a here means a value of that type. What type? Well, whatever type a is in context. If what we have is a maybe live coding language, then just is going to be just followed by a live coding language. So let's work through this now. So we've imported data.maybe. Nothing changes about our live coding language, which is super cool that nothing changes, because had we changed it, that would have represented a really poor decision, I think. And now we've got our live coder. And here we changed our language field to being a maybe live coding language instead of a live coding language. And that's totally a good decision, because it makes sense. Like that's what we were trying to do. We said, if you listen to our description of what we were trying to model, we were like, a live coder might not have a live coding language. And now directly in the definition of the live coder, we've encapsulated that idea. Like we're doing good there. That sounds right. So now we have to change we made 3 live coders, and this isn't going to work anymore because supercollider isn't a valid maybe live coding language. Just supercollider is. But actually I'm going to change my answer to being nothing, because I don't have a preferred live coding language. And Luis, let's keep you still on tidal cycles, and Jessica will keep you still on Hydra. But we're going to preface those constructors with just now. So now our 3 live coders are all valid values for live coder, the type live coder. And our ensemble is still going to be fine because we didn't change anything about that. And we're going to have to change the way our cool factor, our ensemble cool factor works, because now what is stored in each live coder is a maybe live coding language instead of a live coding language. So we can't apply cool factor to a maybe in a straightforward way. So let's solve this reorganization of ensemble cool factor in several different ways of increasing nuance, let's say, increasing sophistication. So one way we might think of solving this would be to make a function called cool factor prime that goes from a maybe live coding language to an integer cool factor. And so we're going to have to cover at least 2 cases here, right? We're going to have to cover the case where we get a just value and some language, which I'll call L. And we're going to have to cover the case where we get a nothing value. And so we might think of giving a 0 cool factor to nothing. Or we could give a 20 cool factor to nothing. Well, let's go with 0. I'll be self-deprecating. And in this first case, where we get a just value, the type of L here is live coding language. And we already have a function, cool factor, that goes from live coding language to int. So we can just use that here. Cool factor L. So this kind of pattern matching, it's like we're using the pattern matching here. It's like we're using that to extract the L value from inside of the maybe to do something with it. And then up here in our previous ensemble cool factor, we could replace cool factor that works with live coding languages with cool factor prime that works with maybes. And we'll load to check if we're okay. And we're okay. And if I go for ensemble cool factor, Reggaetron, it's 17 now because the cool factor went down because of my stubborn ideological insistence on the equality of all languages. Sorry. Being cool is not all it's cracked up to be, anyway, at the end of the day. So anyway, that way was okay. That works. It has the benefit of being quite transparent about how the maybe type works. So you'll see that kind of matching all the time, where people write a function, one for matching the just values, and another, corresponding definition for matching the nothing values. So you're basically very explicitly saying how you handle the case where the thing is there and how you handle the case where the thing is not there. The data.maybe module provides a few other ways. So one is the function maybe. And the function maybe, if we look at its type signature here, it takes a default value of type B, a function from A to B, and a maybe A value. So in this example here, like relating these types to what we were just doing in our example, our B's would be int, because that was the sort of type we were getting out of things. Our A's would be live coding languages, and our type that we were working with was a maybe live coding language. And from that we get a B. And the way it works is if the function is provided, if the maybe value that's provided to the function is a just, then that function A to B gets applied to give you a B. And if it's a nothing, you just get the default value, the first B. So it makes sense. And it's kind of the same thing, right? It's the same thing as what we just did with this pattern matching here. We're saying like when it's a just value, do this. When it's a nothing value, do this. So let's rewrite our answer here using the maybe thing instead. So first attempt, cool factor prime x equals maybe, and I'm just going to scroll this down so we can keep the definition of the type signature of maybe in front of us. We need to provide a default value for when it's given a nothing. That's 0, right? We need to provide a function that goes from A to B. In other words, a function that goes from a live coding language to an int. We already got that. It's called cool factor. And we need to provide the thing, the maybe value, which is called x. There we go. We're done. So our two lines became one, and it's a little bit more clear. Maybe, right? A little bit more economical anyway. And some of you may notice that there's a chance here for us to be extra Haskell-y too, right? Notice how there's an x on the end only and an x on the end here. So if we want to be super cool and hang with all the cool Haskell kids, we can do this instead. It's the same thing. It's the same thing, just cooler. I don't know that we need to develop that much further, but let's take a look at some of the other convenient functions that are provided in the data.maybe module, because working with maybe values is super common, right? Like there's so many situations in life, in programming, where at some level there's, let's call it unreliability, like where things are probably there, but they might not be there, and you need to process that and manage that in some way. And maybe types are just like an awesome abstraction for handling that situation, right? So it's super common. So we have a function that, given a maybe value, tells you true or false, whether it's a just or not. Same thing, telling you whether it's a nothing or not. These functions are interesting. From just and from maybe. So from just will take a maybe value and it will extract the whatever is inside the just values. But if you give it a nothing, it will throw an exception and everything will crash. So this is sort of dicey in a way. You would only ever see from just and from maybe used in some setting where the programmer can be absolutely sure that there's no possibility of the wrong side of the type existing there. And even then, I'm not sure it's really good style. Like, it seems safer to me to just use one of the other abstractions where you're forced to handle both cases in some way.
Well, if there was going to be no nothing, then why did you use just in the first place?
Perhaps, yeah. Yeah, exactly. So the comment was, if there's going to be no nothing, why did you use just in the first place? I mean, I think the way this problem comes up in practice is that people are dealing with big systems, and so there might be a value that's a maybe value that comes in from somewhere, and now they're having to you have to handle both cases, and you have to do something with the value inside it. And for whatever reason, notational convenience, they want to just use some existing function that works on, like they want to compose something together with some existing function that just works on the value contained in the maybe. So it's like, oh, we'll just put a from just in front of it to extract it out. Which, if you're sure you've already covered the other case somewhere else, I guess is okay, but yeah, it seems dicey to me. Jamie, you have a comment?
What if you want nothing to throw an exception?
Sure.
I guess you could put another exception.
Sure. Yeah, so the comment is that perhaps that would be okay if you actually wanted nothing to throw an exception for some reasons, to tell you that there was a problem in your thinking about what you're doing. Yeah, perhaps. Okay, these next ones are a little bit more useful, I think. So from maybe, for example, takes a maybe value and a default value. And if you get a nothing, you get the default value. If you get a just, you get whatever was in the just. So that is kind of similar to what we were just talking about. If the default value makes sense in the situation, there are many situations where it doesn't. List to maybe takes a list, and this is kind of odd. It extracts the first element of the list if it's there and puts it in a just. Perhaps more commonly used is maybe to list. Cat maybes. So if you have a list of things that are maybe there, it gives you a list of just the things that are there. So we can actually do this. I think we can do something useful with cat maybes. So I'm gonna put it down here, and add it. We could define another faction. Let's say that with our ensembles, we wanted to know what are the languages that they use. So we'll call it what languages, and it'll be a function from an ensemble to a list of live coding languages. Now, we could develop this from the ground up laboriously, as we've been doing with some of our examples, but let's go for broke here and go straight to the higher level solution using cat maybes. So cat maybes, we need a list of maybe A's, and from that we're going to get a list of only the just values. So we need to get a list of maybe A's of maybe live coding languages from our ensemble. Now, if you remember, our ensemble is just a list of live coders, and each live coder has the function language. And we've already seen here that there's this function map that lets us apply a function to every item in a list. So thinking out loud here, if we do map language onto our list of ensemble members, that's going to be a list of maybe languages, list of maybe live coding languages. And then if we apply cat maybes to that, we will have a list of the live coding languages used by the group with the nothing values, like me, filtered out. Still loads, and if we ask for what languages, Reggaetron, Tidal Cycles, and Hydra. We don't need to hear anymore about my ideological crusades. What else can we get out of? There's a few more useful things here. Map maybe. So the map maybe function is a version of map which can throw out elements. In particular, the functional argument returns something of type maybe b. If this is nothing, no element is added onto the result list. If it is just, then it's included in the result list. So that suggests another way of doing what we just did, doesn't it? Let's leave it down there so people can look at it. We can make a different version of this that looks like this. Because language is already a function from a live coder to a maybe live coding language. So it fits this A to maybe B type signature. A is a list of live coders. We're good. And from that, we're going to get a list of any of the just values contained in their language field. And once again, for the cool Haskell kids, we should write this like this. But all three are the same thing. Yeah.
It's showing me an error for deriving.
It just has to do with indentation. So if we go to line 20 and scroll over. Oh, not indentation, actually. It's the extra bar you have there.
Oh.
The bar separates the different constructors, but you have no more constructors.
Thank you.
Sure. I have made that mistake like literally 13 million times in my life, so it's easy to spot.
And now through like a lot of errors.
Oh, yeah?
I'll figure it out.
Okay. So we'll probably come back to maybe in a slightly different way later. But before moving on, any questions about maybe? Well, let's move on. So another of these kind of like really fundamental Haskell types that take other types as their argument as a type variable that gets used a lot is called either, and we're building on maybe here. So when you have a maybe type, you're saying you might have this thing or you might not. You either have the thing or you don't. If you have the thing, you have the information about it. If you don't have the thing, the only information you have is that you don't have the thing. So that covers some situations, right? But there are other common situations where you either have this or you have that. For example, let's say there's some type of computation that can succeed or fail. If it succeeds, the value that you might be interested in might be the result. Like, let's say I'm looking for a number. I have some computation that like computes a number from some data somewhere. I might be interested in getting that number as the result. But let's say for some reason something goes wrong. Well, we could represent that with maybe and like with a nothing, but then we'd have no information about what went wrong. That seems kind of crappy, right? We probably want some representation of the error, like an error message, a string even, a string that is like an error message. And in fact, that example that I just gave you is the most common way that either gets used. It's like either you get an error message or you get the thing that you are looking for. So let's look at the documentation for data.either in Hackage. And this looks a little bit different again than what we saw with maybe. So if you look at the data declaration itself, it's got two type variables now, A and B. And conventionally, the A is called the left and the B is called the right. And the type A has a constructor called left. So instead of just A, it's left, or instead of just and something, it's left and that thing. And there's another one called right. And I suppose that this is an incredible example of Anglocentrism in a language's syntax. By convention, the interpretation of it is often that the right value means something correct, and the left value means something incorrect. So, or like an error. It doesn't have to mean that. You can be used any way you want, but that's a super common pattern. That the right value is, it's a pun, right, on the English word right, which means on the right, but which also means like correct, valid, right? So very Anglocentric, but there you have it. Kofi?
There's no Boolean in Haskell?
There is. It's called bool.
Oh.
Yeah, yeah.
And there's if and if else as well in Haskell or not?
Yes.
Okay, just because this looks maybe this. It looks like it's similar, I guess, but has like a minute difference. And
Yeah. In fact, I think it's more different than you might think at first.
Okay.
Let's keep looking at it. So anyway, so we have either. It has two types. When you have an either value, it's either a left or a right. If it's a left, it may contain something that in some sense represents error or failure. If it's a right, it contains something that may represent success. I say may here because nothing stops you. You don't have to interpret either this way. If for example, you did have something that just had like two possible, like it was a fork in the possibilities, I don't know, like let's say we're making a type to represent weather, and there's two possibilities, like it's a sunny day, and when it's a sunny day, you care about the temperature, or it's a rainy day, but on rainy days you don't compare about the temperature. You care about whether, like, you compare about how heavy the rain was in some qualitative measure. So those are two different types. Like the temperature is a number, the quality of the rain is a qualitative type. So there are two different types. There's a kind of example of an either type being used in a way that doesn't represent success versus failure. So in that case, you could use either side, left or right, I think, as a valid representation. But that said, like 99% of the time, either is about success or failure, where the left values, the failure values, are error messages or something else that helps you like deal with the unpredictability of the world. So we've got some functions here. Maybe let's come back to that in a second. Let's think if there's some way of using an either type in our representation of the live coding universe. Well, we could. I know. I got it. Our language. So what if a live coder, instead of maybe having a live coding language, they either have a standard live coding language, or they're too cool for school and have their own custom named live coding language that doesn't fit into our little cozy bureaucratic system. There we go. So again, let me reiterate the principle here. So I might think, so let's say that that's what I'm trying to model. I might go back to the live coding language, and I might model this by adding a new constructor called like custom language, followed by a string. Well, that's not terrible. It's not awful. Like, I can see that working out okay. This is different than our other example, right? Because here, what we've added to the model of the live coding language, it still is a live coding language. Like, we haven't broken the semantics of this type in any way. It's good still. It fits. But let's not do it anyway. Let's do it the other way so that we can use the either type. So we're going to leave that as it is. And we'll say that a language is either a string representing their custom language, or it's one of the standard live coding languages represented by the live coding language type. Or what if, let's make a little jump here. What if it's another type altogether called a custom live coding language, or a custom language? So now we'll have to define that type. And let's say that custom language, let's do this first. Type custom language. It's a tuple with the name of the language and the cool factor of the language. We'll probably come back and do this a different way in a few minutes, but let's start here. So far so good. Now, when we determine the ensemble cool factor, cool factor prime is not going to be any use to us anymore because it works with maybe live coding languages. What we have is either custom language or live coding language. So we need some kind of function from either custom language or live coding language to int. We need that function, and we'll call it cool factor double prime. And cool factor double prime, we're going to figure out what that looks like. So again, we can do it the low-level way first, and then we can do it a cooler way. So we might have a left value. We might have a left and some custom language x. And actually, our custom languages right now are tuples, right, of a string and an int. So we'll make this L for the name of the language and CF for the cool factor. And the cool factor is what we're trying to get, so that's what we'll give back as the answer. We might get a standard live coding language, a right value, in which case we can call cool factor, the original cool factor, on that value. And that's it. We've covered both. We've covered all the scenarios there. What languages doesn't work anymore either, because isn't going to work for us because it uses map maybe, and so it's assuming that language here returns a maybe, is a maybe, but it isn't. It's an either. So we're going to have to change what languages as well. But let's not do that right now. Let's just make a note. Need to change this as well. We're not actually using it for anything anywhere else, so as long as we don't use it, we'll be okay. Let's just check that what we did with cool factor makes sense. Oh, a bunch of errors here. So usually when you get these chains of errors, it's often helpful to go to the beginning, because sometimes the first one also cause the later ones. Not always. So 31, line 31. Where's that? Oh, right. So the error here in line 31 is that we're in our 3 live coders, we're still using maybe values, but we changed the definition of a live coder to be either values instead. So yeah, that's not going to work. So my language is going to be left, and I'll reveal the name of my super secret language I've been working on the last few days. My language is going to be the left value punctual. Oh, actually no, it was a string and a cool factor, and I mean, let's be honest, the cool factor is pretty much off the charts, but we'll call it 11. And now Jessica and Luis are just using other people's languages, sorry. So they're going to be right values. So, and that maneuver that we just made there, where we had just values when we were organizing our thoughts around maybe, and now we have right values with the same thing. Like, that happens sometimes when you're reorganizing code, because like at one point someone was like, oh, we don't really, maybe is good, we don't need anything more than that. And then later they're like, yes, we need something more than that. So all the just values become right values. That's quite common. So those should be good now. Let's see if we're okay after those fixes. No, there's still at least, there's 2 things wrong. 50. Oh, right, here, ensemble cool factor is still using cool factor prime. We need to use cool factor double prime. And we'll try again, and there's still 1 error, 68. Oh yeah, so here we do need to change this now, because even though we're not using it, map maybe, we're using map maybe in language, but language doesn't give us a maybe value. So that's invalid, it's complaining, right? So, and I think we're kind of seeing here in the strictness here, like we're not using this thing, but because it's defined incorrectly, we're still getting errors about how it's defined incorrectly. I mean, I think this strictness and this rigor is one of the things that makes working in this kind of language helpful. Like, it really doesn't let you get away with anything. But I'm going to get away with something anyway. I'm just going to comment out that whole block, because it's hot and it's the afternoon and I don't care. So there we go. Now the bad code is quarantined off and won't cause any problems, and we're good. I'll just make, maybe I'll be a good programmer. I'll just make a little note and say, this doesn't make sense in my comment, so no one accidentally uncomments it and thinks that it should work. Okay, so now if we do ensemble cool factor, we get 28 because of the inclusion of my ultra secret new custom live coding language in the ensemble. And we've used either. But so what we did there with either, that's okay. But I bet you we can do that in a more straightforward way. Let's look at data either. So remember with data maybe, there was a definition maybe, like lowercase maybe, that provided an easy way of dealing with maybe types with both possibilities. Well, also with either, there's a definition called either, lowercase, that provides an easy way of handling both cases. And it's basically the same as the maybe definition, right? Except that maybe the first argument was a default value. With either, the first argument is like an A to C. So it's like, because your either values, they're either A's or B's, left or right. For the A's, the lefts, you convert them to some third type. For the B's, the rights, you convert them also to some third type. And in that way, you get back a common type, a single type that you can use for something else. So either is what we want here. Our A's are custom language. Our B's are live coding language. Our C's are the int cool factor that we're looking for. And we can rewrite this that we did here now as this. Cool factor prime prime x equals either. And now here we provide a function for the left values. I'm just going to put that in a question mark for a second. And then we have to provide a function for the right values. We know what that is. It's cool factor. And then we provide our value. So let's go back to this missing function for the left values. Our custom language is a tuple of string to int, where the int is the cool factor. So we've actually already seen a function that gets the second thing out of a tuple, right? Does anyone remember what it was called?
SND.
Second, right? SND. So, and if we look at the type of second, given a tuple, A and B gives you the B. So it's like from this thing to that thing. So that actually matches what we need. Oops, wrong one. Where'd data.maybe-either go? Here it is. So if we look at A to C here, AB, our tuple, is what the A here is, and the B here is our C here. So second will work. We can put that in. And let's just go right ahead to being cool Haskell kids. Once again, we have x on the end and x here. So we can just leave that off and partially apply either to get the same thing. And we should be good. And when we do ensemble for cool factor on Reggatron, we get the same answer again. But now we've done it in a more Haskellian way. The solution that we've come up with here for cool factor double prime is certainly the best one, the way that we've organized things. But while we were developing it, it occurred to me that there could be an opportunity here to show another route that we sometimes have to go. In this case, it was easy because our custom type happened to be just a tuple, and the thing we were interested in happened to be the second thing, so we were able to use that second function. But what if it wasn't so straightforward? This is a case where often it's really useful to use what's called a lambda expression. Now, a lambda expression is like a function without a name that we write in place somewhere. And in Haskell, it looks like this. So I'm going to rewrite this a third way, where instead of using the second function, I'm going to put a lambda expression here where I've got the question mark, and then cool factor. So a lambda expression in Haskell, we put a backslash, and then we put the names of arguments that we want, and or things that we want to match. In this case, we have a tuple, so I'm going to call it xy. There we're matching that tuple. And then we put an arrow, just like the arrow we use in the type signatures. And then we put whatever results we want. So this is like a function from a tuple xy to something. And we want the second one, so we could put y there. And we actually don't care about the first one at all, so we could put an underscore there, which is more readable. It's more readable because when you put the underscore, it's like you're saying, I don't care about that. It doesn't matter. So you're not distracting a reader with some variable name that they don't actually need to know because it's not used anywhere. So this is those two things are those two solutions are exactly the same. Obviously, the difference with this one is that we could modify it, and actually, I think we should. Like, let's face it. Like, if you're using your own custom live coding language, that's cool. But if you're using it in an ensemble, that's even cooler. I think you should get even more extra points for that. So let's model that here at this point in our structure. Let's say that, let's use our lambda expression here so that when you're using your custom language in the ensemble, you don't get y points, you get y squared points. So now when I reload it, and now when we get the ensemble cool factor, we're up to 138 for using a custom live coding language in an ensemble. Extra points.
Now you can be in by your code.
I'm making a strong argument for it here, aren't I? Well, just like we did with maybe, let's take a quick look through the other functions that data.either provides. I'm not sure if we'll develop them. So there's a function that given a list of ethers gives you just the lefts. Function that given a list of ethers gives you just the rights. Is left tells you whether a value is a left value or not. Is right tells you whether it's a right value or not. Now, just like we had from just in the maybe one, we have from left and from right. And just like we said, with the maybe, that using from just is maybe a bit dicey, because if you get a nothing value in it, it's going to just stop. It's going to throw an exception. Same thing here. If you use from left and you use it on a right, you're done. Your program is done. And vice versa. If you use from right and you give it a left, you're done. Everything's going to stop. So maybe we want to be careful and not use those. And finally, partition ethers, which is really just an expansion of the ideas above. Given a list of ethers, it gives you back a tuple, which is a list of the lefts and a list of the rights. These are all really just different ways of organizing the same ideas. So that's data.either, and it's pretty useful. How are we doing? Time for another short break? Yeah? Let's take an 8-minute break. And let's start again at 4:15. Any comments or questions from our online participants? No? Yep.
It's giving me this error.
29.
Maybe because of this. I mean this.
So let's look. Couldn't match expected type either custom language, live coding language, actual type either custom language, live coding language. Can you go? Can you go to 100? So and then can you go to wherever cool factor double prime is applied? Yeah, it's just the type signature of 124 there. It's right. Yeah, so if you look over there, you're just missing the arrow to int on the end. Yeah. So yeah, sometimes you can get weird error messages when you yourself have declared a type that is not the type of the thing, right? Because now you're telling it like two different things at once, and so the error messages kind of go all over the place.
Yeah, I was like, there's no problem with this thing because it's exactly what
Yeah.
I wrote.
Use that first.
Yep.
Yeah, you could use like Sublime. Free version.
Same thing. So look, cool factor prime should be a function of some of the either value to int. So look at
But I'm able to find that.
see,
That's one
it's just the
has
type signature.
the type on it.
See? Yeah.
Oh, okay, yeah. So,
No, see. Probably.
Unless
there's something else.
I feel like my main is because I have a manufacturer. But it drops a lot of energy in my app. But I don't know if it's I feel like it's just like look.
See? I don't know, try it again.
So it's telling me line 89, so go to line 89.
Yeah, have a lot of packets?
Oh, no, cause I have 16, cause that's a
Yeah.
You're
You're not using
so far
all
as
those.
like, but
You
like,
I think
just
it's two factor prime prime,
just,
you're using the either now, right?
I know.
The either has a prime prime for it.
Yeah, maybe.
Like,
I just had to like reconfirm it.
Or do
So
you
what?
have, what's that untitled, like, file you have open there? Cause if it's like a.
You know, and like one of the virtues of this strict style of programming too is that
Right.
Gradually building up and test them.
This is
To
just-
some
oh,
extent,
no, it's working.
just the fact that it
Before
compiles
was
shows you
before
that
was
it's probably
from
correct.
scratch.
Yeah, because you have all these like checks
Mine's
and
like if I
safeties
open,
already, right?
I guess that's the point.
Yeah.
like
I mean,
accidentally open like a.
I don't want to
site
trap it,
or
but
something,
stuff still goes wrong.
Then it has all the like the binary stuff, but it.
Less often.
But
Cause
it's
I know,
huge. and,
cause I know that happens to me with like whenever I use like subtitle multimedia thing, but I forgot that I could actually do that actually. That's actually very true.
It's kind of
Even not even things I'm more power than most of my like my multimedia programs. It's just like luckily I have enough RAM.
So they're going to secondary school.
Yeah.
And so I'll probably be seeing you in 2 games.
No, I'm not in comp sci. Or
Oh yeah, you're
software.
not. Yeah, you're in sci.
I've integrated by my engineering. But I'm doing my first comp sci minor, so I'm probably, I don't have enough electives to take it in second year, but I'm gonna take 2 and 3 third year. Are you teaching?
I had TA.
Okay, nice.
But if there's any comp sci class you should take, I would recommend that one.
Yeah.
I think that one will provide you with so much comp sci and so much logic that you'll be able to take math classes and to take computer science classes and not have too much things to worry about. Also, your knowledge of Haskell will only make it easier for you. The fact that you know Haskell will make that class easier. We don't teach Haskell, but
Not even in one JC group, it's not like functional programming.
that one teaches Haskell. But I mean,
Hello?
2DM3 doesn't teach Haskell, but it teaches equational reasoning using inductive types, which is all that Haskell is. So a bunch of students were like, when are we ever gonna do this? And then I just opened up Haskell, like, they're like, yeah, that's pseudocode. I'm like, no, that's actual. So Haskell might make it easier for you, but you'll if anything, it will make you a better programmer to GM3, and it will make you more comfortable with Haskell and be able to prove more things with Haskell. And then if you ever want to take any math classes, then you won't have to worry.
Yeah.
I know these
Yeah,
if you
I'm
guys
sure.
take at 2DM3, then they wouldn't take math classes, and then they asked the math professor if they could do their proofs in the 2DM3 style. And the prof said, yeah. And I am kind of the prof saying, like, I like it. And they write every step explicitly with hints and
Yeah.
and then it's a gateway into getting to some of that other places. But
Yeah, like next year I am taking 2Z3 and 2Z3. Like 2Z3 comp sci software. When I take it, stuff like discrete math. The regular entry format takes 2Z3. So I was like combining everything, like I was taking anatomy and stuff.
yeah, it's quite hard.
Yeah, that's what I've heard. So I'm also like, it's not too bad. It's hard to start, so I'm not very scared. But no, in summer it was really fun. Like I didn't need to do that much Haskell work, but like doing idea and stuff. Like I need like a little bit of the stuff.
Yeah, it's going to be fun, but also it's going to be very fun.
Let's see, I have to move out.
Once a month.
Wait, which university is
Sorry.
Okay, yeah, I think it might be. I think it might be.
No, I'll stop around about it if you know about it.
I will eventually make sure he knows about it.
Okay,
It's
good.
fine.
You
It's
can let me know when
manageable.
it is, and if it
Yeah,
works
well,
out
I
with my
did it
schedule,
for
I'll for sure.
I think it's gonna be once a month, like 2 days.
but now
Like it's
I know
every Tuesday a month.
So that's like every year, because like
I
they come and do
think-
everything
I think
for you, like
it's-
senior have.
Yeah.
Okay.
Like they do everything.
Yeah, I'll ask them.
I never was on rest, so I couldn't ever do on my own too.
I wanna do other things, like that's
It's
just the plan for them.
good. Like,
And
like
my
I'm
point
the
is, of course,
coolest,
like,
I'm like
in, you know,
obsessive.
So that I'm like
Cleaning, like, it's
love
not
it,
okay.
can go
It's not
further.
okay.
I never
But-
really did like that though.
Functional programming.
Yeah, well, it can be a good thing or a bad thing. Because they can do too much. I think I'm that way. think I'm too much when it comes to like the
But
organization.
Haskell,
if you
no,
force me to do it,
I would never I would
If you
rather
do
do it
yourself.
for, I would rather do it just because you're gonna ruin, not you. The rumors is gonna ruin everything.
Yeah.
I live with my brother, so I do everything for him too, because if he does something, he's
I don't
gonna
know
ruin
if
it.
you used monad
Logic.
implementation.
Yeah, I did.
So,
So I don't know why like that I would be like, come on, how do I do everything for
So
you?
maps and things, right?
I mean, maps, I guess,
Controls these things.
the shared
They
areas,
exist in
Yeah,
C# as
yeah,
well. And they're
Yes.
called
Yeah, the
library.
rooms.
the rooms I would leave you to, unless you're like too much, I would have to do it for you.
These things are
Okay,
pretty
I'm not like
so
super, I'm not like that, like I'm just
show up and learn.
on me, like I was always children.
Mhm.
Are you here to see what they're teaching or?
I'm here to learn. I think this is cool stuff. And I looked at the schedule, there's a bunch of stuff. I don't actually know Haskell.
If you find someone who's just
That's why I'm.
like, I think my dream is if I don't live with my brother anymore, I would love to find a person who's like me, but I know there's no one like
Give a
me.
presentation on it once a
Okay,
month.
I'm just nuts.
You never know
Other people
though,
might be there
right?
and they might
Like,
ask me why,
a person
what do things mean, and they'll have to learn.
look.
That's a good way of learning.
Maybe, yeah.
Not
Or
actually really work on Haskell.
All right, shall we get started again?
You can never know.
Learning Haskell.
Last little section here today.
I just read the last chapter of the last night. I haven't read it yet, so it's my last one.
So the last thing I propose doing today is just looking at another common data structure, because it's basically what maybe and either are. Is they're like very general purpose data structures that we can use around our own custom data structures to add extra semantics to whatever it is we're designing. And this one, the last one I want to look at today, is the structure of the map. And if we go to data.map in Hackage, there's actually two versions of this module, data.map.strict and data.map.lazy. I don't really want to talk about that right now, so let's just go to let's just click on data.map.lazy, and let's just pretend that that's data.map as far as we are concerned. It is the default, in fact. So if we were to do in our code here, if we were to import data.map, we'd be importing data.map.lazy. And so maps are like lists, but unlike lists, which we've already seen, every item in the list has an index, a key, that is its address. So lists sort of have addresses. Like if we have a list of items, we could say, get me the first thing, get me the second thing, get me the third thing. We could say that. Like we kind of do a lot of the times, and in other programming languages it's quite common for lists to be treated that way. For example, arrays, kind of like that. But a map is something a little bit more generalized than that. In a map, it's like we have a collection of things, and the things have a type, and their addresses have a type, and the types don't just have to be aren't just like positions necessarily, right? They're the types of the keys, the types of the addresses are anything that can uniquely identify a position, right? And the types of the values can be anything as well. So consequently, if we look through the documentation here, when we get to the data declaration for map, it's got two type variables, k and a. And they've chosen the letter k there quite deliberately to mean key, right? So like map ka is a map from where each of the items in the map is referenced by some key of type k and contains some value of type a. The keys might be numbers. They could be, if k is an int or something like that, but they could be something else too, if we wanted. And then there are some functions for making these map things, and some functions for querying, altering, producing new maps from old maps, that kind of thing. So we can start to explore this a little bit. A really common way of making a map A lot of this stuff, you'll see there's quite a lot of functions here. It gets kind of nitty gritty. But a really common way of making a map in practical Haskell code is using this function from list. And so if we look at its type signature, we see that it takes a list of tuples, where the first item in the tuple is the key value and the second value is the thing to be stored at that location, and it gives you back a map of that type. And it's got a constraint. We haven't used that word yet here, although we've started to use the concepts. Everything before the double arrow here is called a class constraint. So if you look at it, before the double arrow, it says ord k. So what that class constraint is saying is, in everything that follows, everywhere I use a k, it can mean any type, but it has to be an instance of ord. And so this kind of makes sense if you think about it. It's like you got this map, and the k's are your positions in the map, and you want to be able to look up items at different positions. So for that to make sense, you have to be able to sort the keys, right? Like, if you can't say where keys are in this thing, it's going to be very hard to find things. So that's, loosely, that's why there's that ord constraint there. It makes sense intuitively. A way we might apply this in our example that we've been developing all day might be to change our cool factor function somewhat arbitrarily to use a map instead. What if we had a map, we'll call it the cool factor map, and it's a map from live coding languages to ints. So we need to make this map to include it in our code. So I'm going to use from list, just like I suggested. It's a really common pattern. Where'd it go? I just clicked somewhere by accident. There we go. So there's from list. And we need to provide a list of keys and values. So I'm going to make a list like that, and then indent tuples. Give you an example here, that are going to be my pairs. And my keys, my k values, are going to be the names of live coding languages. And my values are going to be obviously ints that are cool factors. So I guess let's copy the same stuff we had from before. So 4, 7, 2, 10. So we've made a kind of a very mechanical translation here. Cool factor is a function from live coding language to int. Cool factor map is a map live coding language int. But conceptually they're kind of similar. But that's just because our cool factor function was already kind of a mapping function. So it's not an accident that when we translate them, they kind of work the same way. Not all functions are so close to maps, right? Yeah.
Doesn't the other number have to be something that's distinctive and can't be the same, or like a reference?
No. So in here, in from, let's look at the definition of from list here. So it takes a list of tuples where the first element of the tuple is a key, a unique key, an orderable key in any case, and values. So the values don't have to be unique. The A's don't have to be unique. Actually, there's no constraint at all on the A's. The keys, they don't actually have to be unique either. They just have to be orderable.
Which we made.
If you look at the definition here, it says if the list contains more than one value for the same key, the last value for the key is retained. And if you remember from the way that the ord class works, it provides orderings like greater than, less than, equal. So somewhere in the guts of from list, there's some case where it's saying, well, if it's equal, then use the most recent one. Use the last one in the list. So actually none of them have to be unique, but our only constraint is that they have to be orderable. Our keys here are of type live coding language. And sure enough, if you remember from our work this morning, live coding language is already an instance of the ord class. So we're good. And this is kind of cool, right? And this is sort of different than a list and different than the common usage of arrays in like everyday imperative programming, right? We're using our data type that uniquely represents live coding languages as the keys for our map. That's kind of cool, right? And it actually, it does provide us some protection. Like, imagine that we were using numbers for this instead, and imagine that the number for SuperCollider was 1, and the number for tidal cycles was 2, and extempore was 3, and Hydra was 4. So then this would look like this, right? It would be like 1, 2, 3, 4. Like, look how easy it is to do that instead. Uh-oh. Like, that's invalid. And if we were using an array, we would probably have an exception. You know, there's all kinds of other settings where using that array structure that we index with numbers would blow up in our faces. But if I go back to what we had here, if I accidentally type supercolliders, like, that's not going to blow up later. It's going to blow up now when we compile it, because we're going to go to load the module, and it's going to tell us, supercolliders? What? That's not valid, right? So being able to have the keys of our maps be our own data types that we define with very strict semantics is super useful. All right, we've got our cool factor map. We just need to use it. So what we want to do is we want to rewrite cool factor using this map instead. So if we look down here in this, we got a bunch of functions for putting things in maps, deleting things from maps, just tons of stuff here. And finally we get to the section labeled query or lookup. This is for just getting stuff out of maps. And there's a function called lookup. That's pretty useful. And there's a function called find with default, which is also very useful. Well, this could be a more substantial reorganization. Let's go easy at first. So cool factor for a live coding language X. Now we have a map called cool factor map. So one first idea might be to use find with default here. So find with default. Let's go to class constraint where whatever type K is has to be a member of ord. That's just normal for the map type. It'll come to seem like second nature after a few minutes here. And then we give it an A, which will be a default value. I guess we could use 0 maybe. And then we give it a key, which would be X, our live coding language. And we give it a map, which would be cool factor map. So we've given it a default value, we've given it a key, we've given it a map of where the K's and the A's match here, the types of the K's and the A's match, and that's going to give us an A, which in this case is int, which is exactly what we want. So we're done. Like, this will work, and if we try to look up a language that isn't in the map, which isn't possible right now because we actually have got our map actually has exactly the languages that we have with no typos, unless there is a typo, which is always possible, but I don't think there's a typo. We're never actually going to get the default in this case. So for the moment, let's not think too much about how it works. Let's just prove that it does work. We'll reload. Oh, ambiguous occurrence map. It could refer to either prelude.map or data.map.map. So I'm glad this happened because this is a really, really common situation that you have to encounter. So the issue is this. You remember that we used a function called map early this morning, right? That function is built into Haskell. Let me go down another tangent here a little bit. I keep saying built into Haskell. Nothing is built into Haskell. I'm going to use more precise terminology from now on, the more Haskell-y terminology. Haskell typically ships with a collection of definitions that are called the prelude. And you can think of the prelude as being those things that are always there. It's like kind of like the standard library in C, or it's kind of like everything that's built into Super Collider if you haven't extended it in any way when you get Super Collider. So that prelude stuff is always there. It's the stuff that's defined in the module in the library called base. So I'm going to stop saying built-in anymore because that's not really accurate. I'm going to talk about things being in the prelude versus being in other libraries. So that's the end of that tangent. But I think that tangent was necessary because if you look at this error message, it helps explain why it says it could refer to either prelude.map or data.map.map. So we know there's a map in the prelude because we used it already. That map is the function that lets you map a function into a list. But look, in data.map, which we're looking at here, let's find it. Well, it's going to find lots of that. Somewhere in here there's a map function. Where is it? Here it is. Traversal. So look, here there's a map function too. And see, it's different. Like if we're here in the prelude and we ask for the type of map, it's A to B and a list of A's to a list of B's. But over here, there's another thing called map, and it's A to B again, but map K to A, map K to B. Like those are different. One map works on lists and the other map works on maps. Those are not the same thing. Okay, conceptually, they kind of work the same way, but they are not the same thing at all. Then they're in different modules. One is in the prelude, one is in data.map in the module data.map. So we've just written map in our code and we've imported data.map. So before we imported data.map, the use of just map below was no problem because there was only one map, the map in the prelude. Now we've imported data.map, so we've got two potential candidates for map here. It could be the one from the prelude, it could be the new one we're importing. How is a poor Haskell interpreter to know what we mean? Well, we have to tell it. So there's different ways of managing this. So one way is just to be explicit. This is often the best solution if there's only one or two places where there's an ambiguity. So here, this is where it was map. We might remember that we want the one from the prelude, right? So prelude.map. Right? Just like the error message, see? It says it could refer to either prelude.map or data.map.map. Well, we know we mean to refer to this one, so that's the text we put there. We're good. That's one way. Like I say, if you have one or two places where this is happening, that's often the easiest thing. It's very explicit. You don't have to think a lot about it to do it. You just think which one you want, and you specify it fully. And let's prove that it works. Our error message is going to go away. Well, no, we got another one. Ambiguous occurrence fold L. Same thing. It could refer to either prelude fold L or data.map.fold L. Lo and behold, there's another fold L in map as well. Well, we still know that we want the prelude one, so we'll do that there. Gets a little ugly, but we're good now. So that was one way we could have managed that. There is another way, and I want to show it to you. So I'm going to go back to just using these ones as they were. And instead, I'm going to change the new stuff I introduced. So another way of managing this problem is when we import data.map, we could import it in a way where the things in it are kind of quarantined so they don't conflict with the other stuff we already have in our namespace. And the way to do this is to say import qualified data.map as, and we come up with some name. Often you'll see people using single capital letters for this. That's kind of a Haskell convention. It's okay. It's just temporary. So let's do that. So I'm going to call it M. And now anywhere I want to use something from that module, I have to preface it with an M and a dot. So we've used it in a couple places. So we used it here, like the constructor map comes from that module. So that has to become m.map now. And we used find with default. So that has to be m.find with default. But that's it, actually. That wasn't too bad, right? And you can also actually do import as without the qualified, in which case you have the choice whether to use the qualifier you provided or not. But I'm not sure if that's more useful. Yeah.
Can we expose just like the ones we want?
Yeah.
Is that-
Yeah. You can do that too. So the question is, can we expose just the imported things that we want? And so we can do import data.map and then in brackets just the things we want, which in this case are the map type and all of its constructors. And we want from list, and we want find with default. And then we should be good. Oh, we got to remove. Now we got to remove the m's. Yeah. And we're good again. So there's different ways of managing that problem. Like, this is a common problem. You need to use names. You need to choose names for things when you're programming. You want to use names that are reasonably informative and not too hard to remember. So inevitably you end up using the same name for different things in different contexts. And so Haskell's module system provides, I think, elegant ways of managing this problem. And definitely, in case this is not clear, you definitely want to manage it with the ways we've just done here, with modules and qualifying things, and perhaps just importing selected things. Those three strategies. What you don't want to do, what you don't want to fall into the habit of doing, because it's bad programming practice, is like just changing the names of things to other names, more obscure names, in order to like that catches up with you quickly. As systems get bigger and more complicated. Well, it's 4:30 and we've done a lot. I don't actually want to develop this example much further. Also because every minute that we spend developing it, I get more worried that people in the live coding community will come in to see this out of context and think that we're ranking their languages. And so, in case anyone is watching this and didn't get that message at the beginning, the numbers were randomly chosen by the audience. I think one thing I did want to say about this example we've been developing, though, in connection with maps, is that when you look something up in a map, there's a chance always that the thing won't be in the map. So if you look at the data.map list of functions, somewhere in here, in the lookup section, the main function that you often use for lookup is called lookup, and you see here that it returns a maybe value. So that makes sense, right? It's like you're asking for something at this position in the map, and what you get is a maybe that thing, because the thing might not be in the map to be gotten. So this makes a lot of sense, right? And it's a very safe way of programming around access to these collections, because your lookup function gives you back a maybe value, and that means now when you're doing something with what you get, you have to treat it as a maybe value. It's very explicit, the semantics around it. And this is different, I think, and more strict than what you often see in a lot of other styles of programming, where it's like you access the array and something might be there or not, and if it isn't, it blows up. Or maybe you do a bunch of elaborate case handling around the array to make sure there's something there at that position. But I think this is a much more elegant way of doing it. Like it's not that you guard your lookup in the array. It's simply that what you get is the conditional presence or absence of some value. Like that itself is a type that you can learn to deal with. So it's more of a pipeline or something like that in some sense. I don't know. I like it anyway. So and I think in our example we made this map from live coding language to int, and we used it in our live coding language to int function by using find with default. But I think if we were developing this system in a little bit more nuanced ways, we would probably allow the maybe value that comes from the lookup to propagate up to higher levels of our system there, and we would handle it in different ways. Maybe. I'm not sure. Whew, that was a lot. How are we all doing? Time for a break. So just, I mean, I think probably people would prefer to have a break before tomorrow morning session. We're only in the morning tomorrow because what we're doing tomorrow is heavy enough that it's, just the morning is enough. But just in case people do want to do some extra reading to brush up on things, the Learn You a Haskell for Great Good book, what we have talked about today is really the first 8 chapters or so. So, if you want some reading as you fall asleep, because you just haven't had enough Haskell for one day, there's lots of stuff there, and probably some stuff that we've skipped over too, that maybe will grab your interest. All right, thank you everyone for your attention, and I will see you tomorrow. Thank you.